Okay. Okay. Hopefully everything is clear. I'm gonna start with the slide. All right. Okay. So hi everyone. I'm gonna talk to you today about the research I've been doing recently with my advisor Mark Wilde and a collaborator of ours, Francesco. The name of which you can see here, the name of the research. All right, so I'm gonna jump right ahead and start by giving a motivation and the main message at the same time. So first of all, I'm gonna be talking about quantum error correction, which is basically a procedure by which you can protect a quantum state from a known source of noise. It's been well known since 1998 that you can look at this process as a heat engine that operates with a feedback controller, right? So since that's the case, what we can do is that we can derive the second law, specifically the Clausius formulation of the second law for this engine, which we do. We also, given that such engines, that is to say heat engines with feedback controllers can operate on a efficiency above the Carnot efficiency limit, which is a result that has been known, we show that there's some kind of a trade-off that will happen for our engine. Specifically, the statement is going to be that for low enough temperatures, if you try to operate on the super Carnot efficiency, as you can see here, the fidelity of the resulting error-corrected state is going to be below 1. And if you want to get a fidelity that's equal to 1, you have to operate below the Carnot regime, below the Carnot efficiency, right? So Gabriel just talked before me. He has a very important work in this field as well. I suggest you look into it if you'd like. It's this reference. All right. So with this said, let me move ahead and give you a very basic and pedagogical introduction into quantum error correction, because that's going to be relevant. Okay, so let's start with the classical version. Assume that you're given a classical bit, right? So it can be either in the state 0 or the state 1. And let's say there's some kind of a bit flip error that can happen with some probability, right? And now the question is, given that you know that this error can happen, can we do anything to preempt this to an extent, right? And turns out that in error correction, there is a way to preempt it up to an order p of the probability error. It's called the majority voting method, which I'm going to be briefly describing. All right, so the key to the method is that since you started with a single classical bit, you add 2 ancillary bits to your system. So now you have basically 3 bits, right? And what you do is that you encode a logical 0 into the 000 state now, and you encode a logical 1 into the 111 state. So what's the point behind that? Well, the point behind it is that if a single bit error happens, then the 000 is gonna change into one of these states, right, where a single bit flip happens to a 1. Or if you start from a 111 state, a single bit flip is gonna happen to any of these states, where you're changing a 1 to a 0, right? And those both happen with probability p, and typically p is small. And the important point to notice here is that those 2 subsets do not intersect. So since they do not intersect, what we can do is that we can first measure the state of the 3-bit system, right? After we do the measurement, we can reinterpret an errored result, such as, let's say, 100, as being really the 000 state. Now, there's a probability that this state has came from the 111, where 2 bits have errored rather than the 1, but that has an error probability of p squared rather than just the p, and that's why we can ignore it if p is small. So this is called the majority voting method, and just to emphasize, it can correct errors up to an order p. So it will error up to an order of p squared, right? Okay, so we can make an analogy to this method when we move into the quantum regime. So when we talk about quantum error correction, for example, we can correct specifically the bit flip channel, which is the quantum version of the bit flip error that you just saw, where the Krauss operators in this case will be the Pauli sigma H matrix, right? But of course, the obvious question is, well, in quantum theory, you're dealing with a continuum of possible errors, not just a single discrete error, which is a bit flip error, as in the classical case. So how can we correct this? Well, you first start by noticing that it can be corrected for a phase flip channel. So for a phase flip channel, you have a channel of this form where a phase flip can happen. And that is described by a Krauss operator, being sigma z rather than sigma x, right? So one thing to note here is that a phase flip channel behaves like a bit flip channel if you look into, if you change the perspective from the computational basis into the plus and minus one basis. So that, with that insight in mind, we can go ahead and actually show very simply that you can correct any error you would like, not just the bit flip and the phase flip errors. And this is the way to do it. Well, first of all, you notice that we can write down any error on a single qubit as a block representation, right? Where we have our Pauli matrices right here. Then we note that one of the Pauli matrices, specifically sigma y, can be written in this form, right? Where sigma x comes from the bit flip error and the sigma z comes from the phase flip error. So therefore, this channel has to be a linear combination of a bit flip error, a phase flip error, and a concatenation of both, which is what sigma y was, right? And therefore, you can conclude that by correcting bit flip and phase flip errors, you'll be good to go for all continuum of possible errors that can happen for a single qubit. That's actually has been shown by Shor in his famous paper. All right, so this is what I wanted to tell you about quantum error correction, which is going to be very relevant. Now, let me tell you about the link between quantum error correction and heat engines with a feedback controller. So here I can show you a basic table. On the left-hand side, we can just start by looking at what quantum error correction does. So you would like to, for example, correct for channels that are typically thermal, right? When you go into quantum computing and stuff like that. So the corresponding element to that within like the heat engine theory would be hot reservoir. You would like to recycle your ancillary system. In our case, those were the two additional bits that we added. And in the heat engine case, this will correspond to using a cold reservoir to do the recycling. For the quantum error correction, we of course need to do error detection and decoding. And for the heat engine case, this will correspond to adding a feedback controller. So you can already see a link between quantum error correction and heat engines with feedback controllers. And this has been well known, as I said before. So then, of course, the obvious question is, if there's a link like this, what can thermodynamics say about quantum error correction? Is there any statement that we can make? Before I go deeper into this, I need to tell you, however, how you would quantify the information gain with the detection step, of quantum error correction. All right, so to describe that very briefly, the formalism that I use is called the quantum instrument formalism, where let's say you have a set of measurement outcomes that are possible. I denote them by big Y, and the one that actually happens is little y. Right. So the corresponding state change after the measurement will be given by the following form, where ny are just completely positive trace non-increasing maps, as long as, of course, the sum over y gives you a CPTP map, right? And this is important because you want to preserve the probability, right? The sum of the probability has to be equal to 1, since the denominator right here is the probability. All right, so this is basically what the formalism says. Now, within this formalism, you can define a quantity called the Grunewald information, I denoted by IG, and it depends on the quantum instrument that you use, that is to say the specific measurement, and the initial state of your system. And it's equal to the reduction in the entropy of the state of the system. As you can see here, this is the initial entropy of the state, and this is the average final entropy post-measurement. So this is the quantifier that I used for measuring information gain, and you're going to see this later on. Now, one important thing to notice, this number can be negative, generally speaking, which is unfortunate. However, if you stick with efficient measurements, then you can show that the Grunewald information is actually positive. So, but by the way, by efficient measurements, I mean that the channel or the map NY has this form. Okay. So with this said, let me go back with the quantum error correction and the link between quantum error correction and thermodynamics or heat engines with feedback controllers. So here's a diagrammatic representation. This is what's happening. So we have the system and the ancilla, right? This is the ancillary system. What we do is that we first encode via some unitary the system and the ancilla. And by the way, the state of the system is the one we care about protecting. So after the encoding, we pass the system through a hot bath, which corresponds to the thermal noise that we want to protect against. And then afterwards, we do the decoding stage, which is a combination of two steps, a measurement step, of course. You have to measure the error, and then you do the feedback, right? So there's a feedback stage there. Afterwards, so that you can recycle the ancilla system, you have to pass it through a cold bath to get back the initial state. And hopefully the final system state will be as close as possible to the initial system state. We want that, remember, because we're doing quantum error correction. We're not necessarily extracting work. Okay, so this is the diagrammatic representation. I can give you a detailed structure of how each engine component would do in this situation. And I think that's important. So let me go over that first. Okay, so here on the left-hand side, you see all the involved systems. This is my main system, the state of which I want to protect against error, right? This is the ancilla system. So by the way, the state is prepared in some mixed state, can be arbitrary, but what I do here is I purify it. The ancilla system is the one that I'm going to use to encode my system with, and it's prepared in some thermal state. I actually picked the temperature of the thermal state to be equal to the temperature of the cold bath because I want to recycle my ancilla system afterward. Okay, so this is the cold bath I'm going to be using for the recycling. This is the hot bath, which is going to play the role of the thermal noise. And it's prepared, of course, in a thermal state with some temperature TH. And also, I have two classical registers. So this is important because when I want to do feedback control, I always have to record the outcomes of measurement so that I can use them for my controlling procedure. Therefore, I need to have those two systems explicitly because it's convenient to do so, right? It will be important for the feedback stage. Okay, so let me just go into detail of how the quantum error correction happens within this representation. First of all, the dots that you can see next to the boxes are representing the systems that are specifically interacting with each other. So for example, in the first box, you see here, there are two dots. So there's an interaction that's happening between the ancilla and the classical register. Here, what we're doing is that we're preparing the ancilla for a measurement. We're preparing the ancilla for the encoding. And we're doing that by doing a projective measurement onto the energy basis. So after that, of course, what we do is that we record the measurement outcome, and we use that to do the encoding of the system and the ancilla, right? Afterwards, after the encoding, we can, of course, pass the encoded state through the thermal noise or the thermal channel. And that happens via a unitary interaction between the system, the ancilla, and the hot bath, of course. After the interaction is done, what we can do is, of course, we want to decode, right? So we take the system and the ancilla and we make a general measurement given by our quantum instrument right here. And this measurement is informed by the initial measurement outcome X. And there's an interaction happening with the classical register Y because, of course, we want to record the measurement outcome here too for the feedback control. So the measurement happens, and then the system and ancilla come out, and then we do the decoding stage, for which we use, of course, the both classical registers for this stage. And afterwards, hopefully, the system state goes on, and since it's generally a mixed state, we want it to be as close as possible to the initial pure state. That's the goal. And also, we recycle the ancilla system by making it interact unitarily with a cold bath. And this can be a swap operation where you swap the where you swap the final ancilla state with with a thermal state, with the temperature equal to the temperature of the cold bath. And at the end, you can erase the memory of the classical registers. So this is how the operation works. Now, with this given, what you can do is that we can do an information theoretic analysis, and you can also do a thermodynamic analysis. And from there, you can get into the Clausius inequality for this specific engine. So the Clausius inequality for this engine looks as follows, where on the left-hand side is what you would expect, right? It's the entropy dissipation from the reservoirs into your system. And the right-hand side, there's an account for all possible entropy changes that you would expect. So this one, the first one is, of course, the entropy change of the system. This is the final state. Of course, the initial state entropy is 0, right? Because we purified the state of the system. This is the average information gain that we had through the measurement stage, the error measurement stage to be exact. The third term is an entropy reduction that you get when you discard the two classical registers, where IF is the final neutral information and E represents the engine, excluding the registers X and Y. So E is the system, the ancilla, the hot bath, and the cold bath. And X and Y are, of course, your classical registers. So this is the mutual information. All right, so that's the third term, of course. And the fourth term is the entropy transfer, or the average entropy transfer to your classical register Y. So this is how the second law looks like for our engine. And just for comparison's sake, I can actually show you a couple of known results. So you all know, of course, Clausius inequality for heat engines, which would generally look at this with like this form, where delta H is the net change of the entropy of the system, right? This is when no feedback controller is present. When you have a feedback controller present, of course, you have to add an extra term, which is the Grunewald information, which is what we talked about earlier. Now, as you can see, both those terms are present. The first term, which is the net entropy change of your system, is present. The average Grunewald, or the average information gain, is also present. We have two extra terms, of course, and that's because we're treating the classical registers explicitly, but also our engine is slightly different. It's also worth mentioning that this result is general. So that is to say, it applies for arbitrary initial preparations of your system and for arbitrary generalized measurements that we conduct in the error correction, in the error detection stage. Just to compare it to Sagawa and Yuda's paper, where your initial state is generally thermal for the system. It's not an arbitrary state, and the measurement stage is projected. Okay, so this is the second law. Now this one has a consequence. So what's the consequence? The consequence, at least one of the consequences, is that you can have an efficiency-fidelity trade-off, which I want to be very precise about, because I don't want you to interpret it incorrectly. So given two conditions, so what are the two conditions? The two conditions are the temperature has to be sufficiently low, where you can see the upper bound here. It's the numerator is the heat dissipated by the measurement stage. The denominator is the sum of the logarithms of the dimensions of the ancilla system and the dimension of the register, the classical register Y, that's required for you to record the outcomes of your error syndrome measurement. So if the temperature is sufficiently low, which means it satisfies this inequality, and if the measurement in it is efficient, because we want to use the fact that the Grunewald information is positive, which is not always the case, as I said. So under these two conditions, what you can show is that thermodynamics can make a efficiency-fidelity trade-off statement, which follows from this inequality. And this is just a consequence of the second law that I just showed you. Just for completeness sake, here Fe corresponds to the fidelity of the quantum error correction. So this is the final state reference of the reference at the system, and this is the initial purified state, right? So you can get an inequality like this. Eta C is, of course, the Carnot efficiency. So the statement is, well, although it is true that you can operate above the Carnot limit if you're dealing with a heat engine that has a feedback controller, our results show that if you operate on that limit, you're going to experience a drop in the fidelity. So your fidelity is going to be definitely below 1. And if you want to operate with a perfect fidelity, that is to say, if you want to do the quantum error correction perfectly, then you have to be operating below the Carnot efficiency limit. So this is the statement that we make for our quantum error correcting engine. Okay, so I'm mostly done. I can do the summary now. So as I said before, quantum error correction is one way in which we can protect quantum states from a known source of noise. So since that's the case, and we know that quantum error correction can be modeled as a heat bath, not a heat bath, a heat engine with a feedback controller, we can derive a Clausius formulation of it, Clausius formulation at the second law to be exact, for this engine. And then the main result is that for a sufficiently small temperature and for efficient measurements, you can claim that there's a trade-off between the efficiency and the fidelity of this engine. More specifically, if you operate on the super Carnot regime, you're going to experience a drop in fidelity. And if you want to have a perfect fidelity, you have to operate in the sub-Carnot regime. That's the main result. And hopefully we'll be posting on arXiv soon, so please stay tuned for that if you're interested in this work. Yeah, thank you. Thank you for listening. And hopefully, if you have any questions, please let me know.
Thanks very much, Arshag, for the very nice talk. Questions from the audience? Giacomo, please.
Hi, Arshag. Can you hear me?
Hello.
Yeah. So I have a question. A very nice talk, by the way, like super interesting. I really liked it. Is this like, if we interpret this kind of like this fidelity as a sort of, I don't know, measure for the precision of this error correcting code, could you see this trade-off relation that you found, I mean, be related to the thermodynamic uncertainty relations?
Thermodynamic uncertainty relations. Can you elaborate a little bit more on that?
Right. So, I mean, basically, that's I mean, they express a trade-off between, let's say, the precision. I mean, they are a more general concept that basically relates the precision of, in the sense of a signal-to-noise ratio of any generic current and the amount of entropy production associated with the process, let's say. Right, but when I mean, they were discovered by Seifert and Barato in 2015. And essentially, they also, I mean, in 2017, they have a paper where they show that when you apply the thermodynamic uncertainty relation to engines under some regimes like steady state, Markovian, blah, 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 then, I mean, they actually translate very simply into a relationship between trade-off between efficiency, power, average power, and the power fluctuations, right? So, I see. So I mean, if you, and they express, I mean, ultimately they express a trade-off between the constancy or like the precision of your engine and the efficiency of the same engine. So I was actually wondering, in light of your comparison, like of your analogy between the quantum error correcting code and an engine, basically, whether, I mean, these two might be related, and like also like if this can maybe add some more information about this trade-off that you said between the fidelity and the efficiency, by also in terms of the kind of generalized entropy production that you have, like all the terms that composed.
I see. Yeah. Okay. Actually, that's a very interesting question. I wish I actually knew enough to answer about it. I think I'm not familiar with the quantum, the thermodynamic uncertainty relations very much, so I can't say much about that. But it definitely sounds like an interesting thing to look at. I'll definitely.
Maybe we can discuss about it later.
Yeah, perfectly fine. Yeah, I'm very happy to do that.
All right. Thanks.